Are you able to see the screen? Screen is visible?
Yes, sir.
Okay. Take this program statement. Assuming that xtal is equal to 22 megahertz, write a program to generate a square wave of frequency 1 kilohertz on pin P1.2. Assuming that xtal is equal to 22 megahertz, write a program to generate square wave of frequency 1 kilohertz on pin P1.2. Note down quickly. Note it down. So we are supposed to use crystal frequency 22 megahertz, and we have to write assembly program to generate square wave of frequency 1 kilohertz on the pin P1.2. Okay. So let us write a program for that. Now, before writing the program, we have to know the calculation part. The calculation part is here frequency is 1 kilohertz. Frequency is 1 kilohertz. For what will be the time period? T is equal to 1 by f. 1 by f is 1 by 1 kilohertz. That will be equal to 1 millisecond. 1 millisecond. Okay. Therefore, t by 2, that is half of the time period. By 2, that is 1 divided by, that is 0.5 milliseconds. 1 millisecond divided by 2, that comes out to 0.5 milliseconds. 0.5 milliseconds. Okay. Now here, the starting value that has to be loaded into timer registers, TH0 and TL0, that is given by T on or T off, T on or T off, T off, okay, on time or off time, that divided by time period. That is, here it is on period or off period is 0.5 millisecond. This divided by, for 22 megahertz, what is the time period? How to calculate the time period? Yes, for 22 megahertz. 22 megahertz divided by 12. 22 megahertz divided by 12. That gives the clock frequency. Okay, that comes out to around 921.6 some kilohertz. Okay, and if you 1 upon 921.6 kilohertz, right, 1 divided by 921.6 kilohertz, that comes out to 0.546 microseconds. 0.546 microseconds. Microsecond. Now this is on time or off time divided by time period. 0.5 milliseconds divided by 0.546 microseconds. 0.546 microseconds. This comes out to how much? 915. 915 clock cycles. 915 cycles. Okay. Now here, the starting value that we want to load is 915, right? It is a large value. It is more than FF. It is more than 255. Therefore, we have to divide this 915 by 5, 915 by 5. So 915 by 5, this will be equal to 183 cycles. So 183 is less than 255. It is less than FF. This we can store into the timer register. This TH value, the timer, this we are using the mode 2 here. For this we are using the mode 2 here for writing the program. So for mode 2, we know that it is 8-bit timer, 8-bit auto reload timer. The starting value that we have to load into the TH register, it is given by FF So this 183, it is nothing but this is equal to B7 in hex. If you convert 183, it will be B7 hex. Okay. So TH will be equal to FF minus B7. FF minus B7. So this comes out to 48 hex. 48 hex. Okay. 48 hex. Right. That means what? The starting value that we have to store in the TH naught register, timer 0 TH, sorry, the starting value that we have to store into the timer register, that is TH naught register, it is 48H. 48H. Right. Now, what is the time delay? We want the time delay of 0.5 milliseconds. That is 0.5 millisecond into 2 is 1 millisecond. We want this time delay. So that is 183 counts. How many counts? How many cycles are there? 183. This into every count. What is the time taken? That is 0.546 microseconds. For every count of the timer, time taken is 0.546 microseconds. Okay, this into 0.546 microseconds, this into 0.546 microseconds. Okay, this into, it repeats for how many times? This repeats for 5 times. This repeats for 5 times. So now check how much it is, multiply and see. 183 is the starting value, B7. Okay, 183 counts it is making. So 183 into 0.546 microsecond. For one count, time taken is 0.546. Therefore, for 183 counts, it is 183 into 0.546. That repeats for how many times? Into 5, because here we have divided 915 by 5 to get 183. So that into 5. So this will be approximately 499.59 microseconds. 499.59 microseconds. Right? That means this is approximately equal to how much? 0.5 milliseconds. 0. If you convert this microsecond into millisecond, it will be 0.5 milliseconds. Now we will write a program. This calculation you understood? Understood this calculation here? Calculation is clear, Bharti?
Yes, sir. Yes,
Bharti?
sir.
Prem Mole?
Yes, sir. Understood, sir.
Prem Mole? Calculation is clear? Prem? Prem Mole, calculation is clear? Taik Mohammed? Okay, fine.
Yes, sir. Yes, clear, sir.
So it is 0.5 milliseconds. Okay. Now let us write the program. Move. We have to store the mod register. We have to initialize that. Move mod comma. We are using timer 0 in mode 2. So it is 0000 upper 4 bits gate C slash T bar M1 M0 are 0. Then lower 4 bits for timer 0, gate is 0, software mode, C slash T bar is 0 for timer, M1 M0. Timer mode is 10. So it is 0 to H. Then move CPL complement to generate the square wave. They have asked to generate square wave on pin P1.2. CPL P1.2, we have to toggle it. Then we have to load R0 register R0, hash 05, 05, because here it is 05. We are dividing by 5 here. We are dividing by 915 by 5 to get 183 cycles. So you have to store that many number of times it has to repeat. Move R0, hash 05. Then we have to now use it as a timer. So move starting value. What is the starting value we have to store? Move th naught, comma, hash 48h. This is the starting value. 48, if you store, it counts for B7 number of times. That is 183 counts from 48 till FF. It makes 183 counts or B7 counts. So th naught, comma, hash B7h, 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 okay, or 0B7h, okay. Sorry, not B7, it is 48 because the starting value is 48 here. From 48 it makes 7 counts or 183 counts to reach FF. So the starting value is 48H. And we have to start the timer. Which instruction you are using to start the timer? SCTB set bit TR0. Set bit TR0. Once we start the timer, we have to monitor the overflow flag using the instruction JNB TF naught TF0, comma, back. Monitor the overflow flag. Once it is overflow, it will come out of the loop. Then once it is overflow, we have to clear the timer run control bit. That is TR0 to turn off the timer for the next round, and also clear the overflow flag for the next round. Okay. Then we have to decrement the count. DJNZ R0, comma, DJNZ R0, comma, okay, R0, comma, where it should jump? It should jump to, if it is not 0, it should jump to again, right? Because it has to repeat for 5 times. If this count 48H, B7 183 cycles, it has to repeat for 5 times to generate a delay of 0.5 millisecond half period or 1 millisecond full period. Once it becomes 0, once the count becomes 0, then we have to repeat it, SJMP repeat, SJMP repeat. So it goes to repeat here. It will complement the first. If it is 0, it is making 1. There is a delay which is given by this timer, right? There is a delay given by this timer, this part of the program. Then again next time repeat means it will come here. Complement P 1.2 means from 1 it will become 0. Then again there is a delay given by this timer, so it will remain low for this much amount of period, okay, given by the timer. Then we have to stop the timing operation. We are using the instruction end to stop the timing operation. Okay, this is a small program. First, we are initializing TMOD register, timer 0 in mode 2. Then we are complementing. We are storing R05 for repetition of 5 times this loop. Then starting value is 48. We are storing. Start the timer using the instruction SCTB TR0. We are monitoring the overflow flag using the instruction JNB TF0, comma, back. Once there is overflow condition, it will come out of the loop. Clear TR0, clear the timer, stop the timer, clear TF0, clear the overflow flag for next round of operation. Decrement R0, that is 5 minus 1, 4. If it is not 0, it will jump to again load the starting value in TH0 and repeat. Suppose if it is 0, it will come out of the loop, then SJMP repeat. It will go to repeat here, complement P1.2, and it will complement the bit or that particular bit P1.2 of port 1, right, from 0 to 1 or 1 to 0, and it will be remaining in that state for the delay given by this delay portion of the program. Okay, that is given by the timer. The delay is given by the timer. Fine. So did you all understand this, students, here? Students, did you all understand here this program? Program is clear. How to generate a square wave on pin P1.2 of 1 kilohertz frequency using crystal frequency equal to 22 megahertz. Taik Mohammed, is it clear? Taik Mohammed?
Yes, sir.
Taik Mohammed?
Yes, sir. Yes. Yes, clear, sir.
Bharti? Is it
Yes,
clear?
sir. Yes, sir.
Bharti?
Clear, sir.
Shafia?
Sir, no, sir.
Any problem here? Shafia?
Sir, I didn't get the logic, sir.
Shafia? I'm not able to listen to you all.
Sir, we can listen.
Just unmute and you can speak. Unmute your cell phones and you can speak. Are you able to listen now?
Yes, sir.
Bharti? Did you understand or it was sound was not coming?
Sir, no, sound
Bharti?
was coming. You was not able to hear us.
Okay, okay, no problem. Then it is no problem. You heard my talk, no? You heard my
Yes, sir.
presentation.
Yes, sir. Yes, sir.
Then no problem. Okay, fine. Thank you, thank you. Mole Prem, did you understand? Mole? Mole? Taik Mohammed? Shafia? Shafia?
Sir, ನಂಗೆ ಲಾಜಿಕ್ ಅರ್ಥ ಆಗ್ಲಿಲ್ರಿ.
ಅರ್ಥ ಆಗ್ಲಿಲ್ರಿ? ಹೇಳ್ತೇನೆ ನೋಡ್ರಿ, ಹೇಳ್ತೇನ್ರಿ. See here. Now they have given the crystal frequency as 22 megahertz. Correct? So crystal frequency divided by 12, that gives the clock frequency. Fine. Crystal frequency is 22 megahertz divided by 12, that gives the clock frequency. Right? How much should be the clock frequency that should be applied for the timer to count? That is this much. Now, if you want to find the time period of that clock frequency, what we have to do? We have to take 1 by f. 1 by f, that is 1 divided by 921 or 921.6 kilohertz. If you do that, it comes out to around 0.546 microsecond. Now, what is meant by 0.546 microsecond? It means the timer will count for every 0.546 microsecond of the clock period or the clock frequency. So every 0.546 microsecond, the timer will count. Getting the point here? Now,
Yes.
what frequency there? Any doubt here, Shafia?
No, sir.
Understanding, no?
Yes, sir.
Okay. Now, what frequency they have asked to generate? Frequency of 1 kilohertz. Correct? So, frequency of 1 kilohertz, if you want to generate, then what should be the time period? T is equal to 1 by f. That is 1 upon 1 kilohertz. That is 1 millisecond. 1 millisecond. Correct? So, if time period is 1 millisecond, what is half of 1 millisecond? That is half period. Half period. Square wave means it is 50% duty cycle. On period is equal to off period. So how much is the half of the period? 1 millisecond divided by 2. That is 0.5 millisecond. 0.5 millisecond. Fine. Now the equation here is T on or T off divided by 2. Sorry, T on or T off divided by T. That is on period or off period. That divided by time period. That gives the number of counts or the number of clock cycles. Right? On period is how much? On period or off period is 0.5 millisecond. Then the time period is 0.546 microsecond. 0.546 microseconds. We have calculated the time period of the clock frequency. Correct? So this comes out to 915 cycles. 915 cycles. Fine. Now 915 cycles means if you convert it into hex, it will be more than FF or it will be more than 255. The maximum value that you can store in the timer register TH0 or that is TH0 register for timer mode 2, it is FF. That is the maximum value that you can store, 8 bits. Right? Here 915 means it will be more than 255. So we have to break this. We have to split it. That is, we are dividing this 915 divided by 5 to bring down the value to less than 255. So that this 183 count, that is in hexadecimal, it is B7. Okay, so the maximum value is FF in the timer register that we can store minus this B7. That means the starting value, if we store 48H in the timer register, it counts up till FF. It counts up till FF. How many counts it will make? It will make a count of B7. It will make a count of B7 or 183 counts. 183 counts. Getting the point here, Shafia?
Yes, sir. Yes, sir.
Okay, fine. So this is the starting value that we have to store, so that it makes a count of 183 counts to reach up till final value. Final value is FF. Fine. Now, if it is 183 counts, then how much will be the time delay? Let us calculate that. 183 into 183 counts. So for one count, how much time is required? 0.546 microsecond of the clock frequency or the clock period. Correct? So 183 into 0.546, it repeats for how many times? 183 into 0.44, 183 into 0.546 microsecond, it repeats for 5 times. So that comes out to 499.59 microsecond. That will be 0.5 millisecond. Okay. So this is half the period. So if you want 1 kilohertz frequency, this is multiplied by 2. So 0.5 millisecond into 2, that comes out to 1 millisecond. Then reciprocal of 1 millisecond is 1 kilohertz. That is what frequency we want to generate. Square wave frequency. Now it is clear, Shafia?
Yes, sir.
Shafia, program you want me to explain?
Sir, no,
Program,
sir.
or is it understood the program?
Yes, sir.
Okay, fine. Fine, good. Mole Prem, is it understood? Mole Prem?
Understood, sir.
Understood, fine. Taik Muhammad?
Sir,
Taik Muhammad?
understood.
Understood? Okay.
Yes, sir, understood.
Good. What about Bharti? Bharti? Bharti?
Yes, sir, understood.
Understood, clear? Any problem in understanding, Bharti?
No, sir.
Okay, fine. We'll continue with some more programs in the next class, right? And we'll take the class on Monday. Okay, that I will inform you when I will be taking the class. Okay, thank you.